What are autoregressive models? Autoregressive models generate outputs by building them step by step. In simple terms, they create one token or value at a time, and each new piece depends on what the model has already produced. Technically, they work by predicting the next token using conditional probability, where each prediction is based on the sequence generated so far. This makes them ideal for language modeling, time series forecasting, and audio generation because they naturally extend patterns over time. Think of a musician composing a melody, playing one note after another, with each new note influenced by the notes already played to keep the tune smooth and coherent. Autoregressive models follow this flow as they generate sequences one step at a time. How do generative models learn complex data distributions? Generative models learn complex data distributions by studying large amounts of real examples and discovering the patterns that define them. In simple terms, they learn how real data is structured so they can create new samples that look or sound similar. Technically, they map data into a latent space that captures important features and use training objectives such as likelihood, reconstruction loss, or adversarial loss to match the true data distribution. Through repeated optimization, the model adjusts its parameters until generated outputs statistically resemble real ones. Think of an art student who studies thousands of paintings, absorbing the brushwork, color choices, and style of a master. With enough practice, the student can create original pieces that fit the same artistic style. That's how generative models learn rich, complex patterns. How do GANs differ from VAEs? GANs and VAEs are both generative models, but they create data in very different ways. In simple terms, GANs use a competition between two networks, where one generates data and the other judges it, leading to highly realistic outputs. VAEs compress data into a latent space and then reconstruct it, creating smoother but sometimes softer results. Technically, GANs rely on adversarial training between a generator and discriminator, which can produce sharp samples, but also risk instability or mode collapse. VAEs use probabilistic encoding and decoding, giving a well-structured latent space ideal for interpolation, but with slightly blurrier outputs. Think of GANs like a forger challenging an expert to spot fakes, while VAEs act like a sculptor who molds and reconstructs forms with consistent internal structure. That's the key difference between them. What are attention mechanisms in generative AI? Attention mechanisms allow generative models to focus on the most important parts of the input while producing an output. In simple terms, they help the model decide what deserves more attention, so the result stays relevant and coherent. Technically, attention assigns weights to different input elements, guiding the model to prioritize the pieces that matter most for tasks like translation, text generation, and image captioning. Transformers rely heavily on this to understand long-range context and maintain consistency. Think of it like recalling a movie. You naturally focus on the major scenes and plot twists, not every minor frame, and those key moments shape how you retell the story. Attention works the same way, highlighting what truly matters. How do multimodal models generate multiple data types? Multimodal models can generate different types of data because they learn how information from text, images, audio, or video connects and influences each other. In simple terms, they blend multiple inputs, so the output reflects understanding across modalities. Technically, these models encode each input into a shared representation space where relationships between modalities are aligned. Using mechanisms like cross-modal attention and transformer-based joint embeddings, the model can then decode this shared representation into any target output, such as generating an image from text or a caption from an image. Think of a storyteller who reads a novel, listens to music, and watches a film, then creates a single performance inspired by all of them. That's how multimodal models create rich, coherent outputs. How can generative models be constrained during training? Generative models can be constrained during training by adding limits that shape how they learn, ensuring their outputs stay realistic, safe, or aligned with specific goals. In simple terms, these constraints act like boundaries that keep the model from drifting into unwanted behavior. Technically, constraints can take the form of regularization, which penalizes overly complex or unrealistic outputs, conditional training that uses labels or attributes to guide generation, gradient clipping or modified loss functions to maintain stable learning, and safety rules that restrict harmful or invalid outputs. Think of a sculptor shaping clay inside a mold, where the mold sets the boundaries while the artist still creates freely within them. That's how constraints guide generative models. What are top K and nucleus sampling? Top K and nucleus sampling are techniques that help generative models choose the next word in a controlled yet creative way. In simple terms, they limit the model's choices so it avoids random or irrelevant words. Technically, top K sampling keeps only the K most probable tokens and selects from that fixed shortlist, while nucleus or top P sampling chooses from the smallest set of tokens whose combined probability reaches a threshold like 0.9. This keeps generation focused while still allowing variation. Think of a restaurant menu. Top K is like picking only from the top 5 best-selling dishes, while nucleus sampling is choosing from the most popular dishes until they cover most customer orders. Both methods keep the selection meaningful. What is prompt tuning versus fine-tuning? Prompt tuning and fine-tuning are two different ways to adapt a pre-trained model. In simple terms, prompt tuning adjusts the instructions you give the model, while fine-tuning changes the model itself. Technically, prompt tuning keeps the model completely frozen and learns small prompt embeddings that guide its behavior. This makes it lightweight, efficient, and effective even with limited data. Fine-tuning updates some or all of the model's internal weights using new training data, allowing the model to specialize more deeply, but requiring more compute and resources. Think of it like working with a financial advisor. Prompt tuning is giving them specific guidance, such as focusing on tech stocks, while fine-tuning is retraining them with new strategies that reshape how they make decisions overall. What is knowledge distillation in generative models? Knowledge distillation is a method where a large, powerful model trains a smaller one to mimic its behavior. In simple terms, the big model teaches the small model how to generate high-quality outputs while using far fewer resources. Technically, the teacher model produces soft targets, such as probability distributions or example outputs, and the student model learns to match these instead of learning from raw labels. This reduces model size, speeds up inference, and preserves most of the original performance. Think of a senior chef guiding a junior chef, demonstrating techniques, timing, and flavor balance built from years of experience. The junior chef soon produces dishes nearly as good, but faster and with less effort. How do generative models handle long context? Generative models handle long context by using techniques that let them retain and process much more information than standard sequence models. In simple terms, they use mechanisms that help them remember earlier parts so their responses stay coherent over long passages. Technically, attention highlights the most relevant sections of long inputs. Memory tools like caches or recurrent attention preserve earlier information, and methods such as chunking, sliding windows, or sparse attention reduce computation for long sequences. Think of a librarian reading a long book using notes and bookmarks to recall important details from earlier chapters. Generative models do the same to keep the narrative consistent across extended context. We have a wealth of content on AI, ML, statistics, Gen AI, and more, tailored for all skill levels from beginner to intermediate and advanced. Wishing you the very best in all your endeavors. I truly hope you found this session helpful and insightful. If this video added value to your learning journey, that is more than enough.